if you have slope that leads to the lower position, you will see that ball actually roll faster and faster, right? The ball actually will gain the momentum, right? So what exactly is that? Basically, okay, the ball will have acceleration, right? You learn from physics, okay? You learn from physics that there's a acceleration, okay, that will help the ball roll faster and faster, right? Okay, but of course, suppose, so this is, if you have if this slope is very long, okay, you will see this ball, the speed keep increasing, but to a point that it will stabilize, right? The ball will not roll faster and faster and forever and to a light speed. It's impossible, right? Why is that? Why is that? I hope you still remember something from your physics class. Even though we know, like in our department, actually we cut down the physics class. I mean, for the undergraduate students, the student in computer science, in our department now only need to take one, 3 credit hour physics, which is it's different from the other like departments. I mean, in the College of Engineering, for example, okay, they need to take like 6 credit hours physics class, okay. So I hope you still remember. The ball keep rolling, faster and faster until it stabilizes. Why does it stabilize? Friction, right? Friction, because there's a friction that will cancel out the acceleration, which make the ball, it's eventually, the forces will cancel out each other, and the ball will enter a state that, you're moving at the constant speed. Eventually, but at least at the beginning, you see the ball keep moving faster and faster, right? Okay, that's the basic physics that you should learn from, or you should see from the experiment, basically. Okay, so this momentum optimization. It has been proposed by this Boris Polyak. Okay, when was that? 1964. This thing was proposed not for deep learning. It was proposed long time ago. Okay, because remember, even though in deep learning we use gradient descent concept, but I have to remind you that gradient descent is a very traditional optimization technique we know about long time ago. Okay, it's just now we use it for deep learning. Okay, but the same concept has been used, in mathematics to find the optimal solution. Okay, long time ago. Okay, so you see this momentum optimization was actually proposed in 1964. Okay. So what's the difference between this momentum optimization and the regular gradient descent? Basically, the regular gradient descent, you say, wait a moment, in a regular gradient descent, when the slope or the gradient is larger, we also move faster, right? Because the gradient is the next location. Remember, the P equal to P0 minus eta, and the gradient, right? Okay, of the current P0, actually. Okay, so let's say this is cost function, P P0. Okay, so this is the gradient of the cost function. So when the gradient is bigger, it's larger. Of course, I mean, you are going to move faster too, okay, in the regular gradient descent concept. So what's the difference? The difference is that in this approach, there's no acceleration, okay? The previous gradient, okay, the gradient you have from the previous step does not have any impact to the gradient to the next, I mean, does not have the impact to like the movement, speed of movement to the next step, okay? Pretty much this, the amount of movement is determined independently at each location, and of course also by the learning rate, right? So that's the primary difference. Okay, here. Okay, this is like the formula I just wrote. Okay, this one does not care about what the earlier gradient were. Okay, if the local gradient is tiny, it goes very slowly. If the local gradient is large, it goes faster. But no matter it goes slower or it goes faster, it is determined by the local gradient. It is not determined by the gradient of the previous location, right? Okay, so that's the difference. Okay, so momentum optimization cares a great deal about the previous gradient. Okay, at each iteration, it adds the local gradient to the momentum vector. You can sort of treat this momentum vector as like a, you know, kind of accumulated speed. Of course, we need to multiply this by a learning rate, eta. Okay, otherwise it's going to go too fast. Okay, and it updates the weight by subtracting this momentum vector. Okay. So, of course, we also incorporate the friction. Okay, we also need to incorporate the friction. Okay, we call that friction. We give like a hyperparameter beta for that friction. We call that hyperparameter as momentum hyperparameter. Okay, so which normally is set between 0 and 1. When this friction hyperparameter or momentum hyperparameter is set to be 0, it means the friction is very large. Okay? If this friction hyperparameter is set to be 1, it means we have no friction. We have no friction. So the default value for this momentum or friction hyperparameter is 0.9. Okay, 0.9. And the formula for the momentum optimizer goes like this. So see, m, okay, is a sign. This m is what we call momentum vector. Remember, I told you that we are going to, you know, accumulate the speed, okay, by this m, the momentum vector. So it's going to be assigned, okay, to be beta m. Okay, you are going to, you know, discount the previous momentum vector by the friction, okay, by the friction hyperparameter, okay, plus eta, okay, the gradient times the gradient, okay. So basically, this is a local gradient, okay, and then okay, you add this thing to the previous momentum vector, okay, pretty much, and this is the resulting momentum vector, and the current location will be the previous location minus this m, okay. So this is like the momentum optimizer algorithm, okay. So you can do a very easy calculation, okay, to see that, okay, you know, what is the the highest possible, you know, learning rate. I mean, or like a, you know, or not learning rate. I mean, the highest possible moving speed. Okay, if you use like if you compare the momentum optimizer with the gradient descent, the regular gradient descent optimizer, you will find that, okay, if beta is 0.9, okay, the terminal velocity 1 minus beta is equal to 10 times the gradient times the learning rate. So in other words, okay, it is going to move 10 times faster than the regular gradient descent. Okay, which is obviously a good thing, right? I mean, when it comes to training the model, okay, because it's going to, you know, the model convergence is going to be much faster, okay. So this allows the momentum optimization to escape from plateau much faster than gradient descent, okay. And also, we see that when the input have very different scales of the cost function will look like an elongated ball. Remember, I mean, we draw that, you know. So I think I draw something like this, right? Okay, so it's like an elongated ball, or I told you like it's kind of like a, you know, the football, okay, the rugby, the ball used in the rugby, you know, which is like you know, cut like by half, okay, from, you know, the long axis, and that means if you are here, then it's going to move something to hit to. My drawing is terrible. It's going to move something like here. Okay, because it's this direction. I mean, it's go. I mean the height go down faster. This direction, the height go down slower. So as a result, you will see the ball actually move in a curve. Okay, and you know, in contrast, momentum optimization will roll down the bottom to the valley faster and faster until it reaches the bottom. Okay, so it's going to be something like you know, it's not going to change this curve, but it's going to move much faster. But so if we don't use spatial normalization, the upper layers will often end up having input with very different scales. So using momentum optimization help a lot. So it can also help roll past local optimal, okay? Because if you roll faster, it's slightly help you to escape from local optimal as well, okay? So this is some benefit that we can have if you use momentum algorithm, okay, optimization. But of course, like, you know, there are also some disadvantage, okay? Just like if you use a larger learning rate, okay, what happens is that, okay, you know, the optimizer may overshoot a bit. I mean, what I mean is like, okay, when you reach this local minimum, it may go too fast and go and to here, and then you come back. So it's going to be, you know, it's going to escalate, okay? Just like if you have a bigger learning rate, it's going to escalate near the optimal location. However, okay, remember in the momentum optimization, we have the friction, right? Having that friction help us eventually stabilize to the optimal location, because learning rate is fixed, So it's going to, fluctuate all the time. But the momentum optimization, because we have the friction, so it helps us to stabilize. Okay. It's just like it will take a while, for this friction to, take into effect and help you to converge. Okay. So in order to implement momentum in Keras, it's very, very easy. Okay. You still call it SGD, but in here, okay, not only you provide the learning rate, but also you provide the momentum equal to 0.9, which indicate the value of that momentum or friction hyperparameter. Okay, so then the Keras will know that, oh, you are talking about momentum optimizer. Okay. So the problem with the momentum optimization is that you have one more hyperparameter to tune, right? But keep in mind that you most of the time you do not need to, change this value. Okay, it is in practice it almost always, goes faster than the regular gradient descent. Okay, you just use 0.9 for this momentum hyperparameter, and you are good. Okay, you should be good to go. Okay. Well, it's about time. So let's take 10 minutes break. Okay. When we come back, we will talk about some more optimizers. Okay.对，那